All right, hello everybody. Sorry I'm not here. I'll try to make this as brief as possible with a few examples and do my best to explain so that there are no questions. Obviously, when I come back, we can go through this more in detail, but uh, the, the lesson for today will be on implicit differentiation. Okay, and so what you need to know is when to use it. Okay, so first, an explicit function looks something like this. F of x equals whatever, right? 3x squared minus 5x. That would be an explicit function. Or y equals 3x squared minus 5x. Those are explicit functions because y or f of x is isolated. It is by itself. Implicit functions would be something like this. Okay, so here's an example of an implicit function. Here's another one. Okay, and all you have to know is that y is not by itself. Okay, in fact, here we have multiple y's. Okay, so you would even say that for this first one that I just highlighted, sine y and y, it would probably be impossible to isolate y and have an explicit function. This one you could probably do with some completing the square and maybe if you really spent some time doing some algebra, but even this would be tough. Okay, but you have multiple y's. It's hard to get y by itself, and even when it's easy. So for example, I'll just go talk about this one real quick. So, and you don't have to write it down right now. I'm just going to show you. So if I ask you to find, oops, dy dx, okay, until we learn about implicit differentiation, which we will here in a moment, what you would try to do is say, okay, I have y squared, I can get y by itself, I move the x squared over, then you square root both sides, then you have y equals plus or minus the square root of 1 minus x squared, and then you say, okay, now I'm going to take the derivative. So if I take the derivative, then you have to use the power rule, 1/2, you got plus or minus. Anyway, I'm already getting pretty involved here. You got the square root in there, it gets pretty ugly looking pretty quick. Okay, so a lot of steps there just to get the derivative of y. Okay, so what you have to keep in mind here, and I'll explain how this works, okay, as soon as I'm done erasing. Sorry, there we go. You want to always assume or think of y as f of x. So anytime you see a y, think of it as a function in terms of x, which we haven't really defined yet because it's within the equation itself, but that will explain some of the steps that we're about to do. Okay, so if I want to find the derivative, okay, so if I want to find dy dx here, first you just take the derivative with respect to x, so that's d dx of both sides. So that looks something like this. So take the derivative with respect to x of whoops, getting ahead of myself, of x squared plus y squared. And then I'm also taking the derivative with respect to x on the right hand side of 1. Okay, so think of it like this. On the left hand side, the derivative of x squared, that's pretty easy, that's 2x, plus, and now here's where it gets a little weird at first, but once you do this a couple times, you're just going to remember, okay? This y, remember, it's technically f of x. It's technically f of x. So if I take the derivative of f of x, it's technically f prime of x, okay? But here, this will probably make more sense over here. So off to the side here for a second. So technically it's like f of x squared. So how do I find the derivative of this? Well, we see a power on the outside, so that's 2 out in front, and then f of x. And then don't forget, we multiply by the derivative of the inside. Always be chaining. We talked about that last week, right? And so technically this here is going to be 2y. And now this over here, f prime of x, another way of writing that is just dy dx. Okay? And so once you see kind of how that works, basically anytime you take the derivative and there's a y in there when you're taking the derivative, you're just going to have a dy dx attached to the derivative. Okay? On the right-hand side, the derivative of 1 with respect to x, there is no x, so that's just going to be 0. Okay? So let me kind of clean this up a little bit. And I'll maybe explain that again in the second example, but so far here's what we have. Okay? So now, after we take the derivative of both sides with respect to x, we isolate or solve for dy dx. So our goal is now to get dy dx by itself. So I can do that by subtracting 2x to the other side. So now it's 2y times dy dx equals negative 2x. And then if you divide both sides by 2y and simplify, you have your derivative. That'll be negative x over y. Okay, and I know that took a while to explain and all that, but this will be a lot quicker than the alternative, which is to isolate y first, find the derivative with all those square roots and using power rule like we were showing initially. But anyway, and now you can answer any application question. If there's a tangent line involved, if there's a tangent line to one of these, maybe we want to figure out what the slope of the tangent line is here. Well, if I give you an x point and you got the equation, whether it's explicitly defined as f of x equals whatever, or if it's an equation that's implicitly defined like this, the rules or the roadmap is the same. Find the derivative, in other words, find dy dx, and then once you have dy dx, you can figure out the slope and go from there. Okay? Anyway, let's try this one. Example 2. So again, we're going to take the derivative of both sides. Well, maybe just let me rewrite it. So I'm going to take the derivative with respect to x of the left-hand side and the derivative with respect to x of the right-hand side. Okay? So here, the derivative of x is just 1 plus, and now remember, think of this, so here's where I'm going to explain again why we have this dy dx popping up. Think of this as sine of f of x. And I ask you to find the derivative. Just like we did with the chain rule. First you say, oh look, there's a sine here. So we take the derivative of sine as cosine, keep the inside the same, and then we have to take the derivative of the inside, which is f prime of x. Okay? So again, that's kind of what's happening here. So we're going to have 1 plus the cosine of, and I'm just going to keep it as y, and now f prime of x is just dy dx. Okay? And so that's the left-hand side. And again, you don't have to do it the way I'm doing over here, that's just kind of explaining more in detail why this dy dx is popping up, okay? But that's essentially it, okay? Anytime you have a y involved, you're going to have a dy dx, or that's where the dy dx will come in. That's what we're trying to find, right? On the left-hand side, this is just going to be dy dx, okay? And again, it's for this, you could even just literally think algebraically. This makes sense now, dy dx. And if you don't like that, again, it's the derivative of f of x. Well, that's the same as f prime of x, but f prime of x is just dy dx, okay? So basically, just remember, if we have the derivative and there's a y involved, you differentiate like normal, attach a dy dx. If I did that here, the derivative of y is technically, is technically just 1, but then we attach dy dx, okay? All right, so now what do we do from here? Our goal is to isolate dy dx. So now what I would do is move all the dy dx terms to the left-hand side. So I have dy dx times cosine of y. I'm going to subtract dy dx, and I'm going to have minus 1 on the right-hand side. So I've taken this, moved it over to the left, and taken the 1 and moved it over to the right. Okay? And now what you can do, and this will be commonly used with implicit differentiation, is factor out dy dx. So if you factor out dy dx, now what's left is cosine of y minus 1 equals negative 1. And so then dy dx, you can easily isolate now if you just divide by cosine of y minus 1. So here's dy dx. Now the thing with dy dx, when you differentiate implicitly like we just did, you might end up with formulas that have y and x or just y's in there, and that's okay. So far we've only seen derivatives with x's involved, but it's okay to have dy dx be written in terms of x and y, especially when you're using implicit differentiation, okay? All right, what I'd like for you to do is pause the video and maybe try example 3 on your own first, see what you can do, and then I'll go through it, okay? And just be careful. Some previous things are going to start to pop up here as you go through it, so take your time and make sure you think carefully before you do each step. All right, so again, I am taking the derivative of everything, the left-hand side, the right-hand side. So when I do that, I get 3x squared plus, this will become 2y, and again, once you do this enough, you just remember, yeah, attach dy dx. Okay, and I've shown you twice now why that's the case. On the right-hand side, we have a product. We have 6x, we have 6x and y. So the pink is going to be my first function, y is going to be my second function. We have to use the product rule over there. So I hope you did that. If you didn't, maybe you can pause the video again, go back and see if you can fix your mistake. All right, but if we use the product rule, so here we go. We're going to write down first function, 6x, times the derivative of the second function, which will be dy dx, plus derivative of the first, which is just 6, and then times y. Okay? And now, just like before, we're going to isolate dy dx. So I'm going to move everything to the left. Let's see if I can do that all in one step now. I'm moving all the dy dx terms to the left, and I'm going to factor out the dy dx. So that'll give me a 2y minus 6x on the left-hand side. So now these terms are taken care of. Now I just need to move the 3x squared over. That'll be 6y minus 3x squared. And so then dy dx will be 6y minus 3x squared all over 2y minus 6x. So hopefully you guys got that. If you didn't the first time, if you made a little mistake with the product rule, I get it. You know, you always got to remember all the previous stuff that we've talked about. It just always kind of gets embedded within certain problems, so you can never forget things like that. All right, example 4. Go ahead and try that one on your own, and I think that's a good one. I don't think we need to do example 5. It's pretty similar to what we've been doing, but this is a good one. Okay, pause it, try it, and I'll go over it here in just a second. All right, hopefully you've seen this type of question enough that you know what to do. You're on autopilot, right? You see tangent line, we're automatically thinking I need to find slope and I need a point, right? I need to know the slope of the tangent line and I need to know a point. Well, the point is easy. Let's find that first. I know x is 2, okay? I'm going to go ahead and plug into x, so that'll be 4 plus 8y, because that's 4x, so that's where I'm getting 8y from, is equal to 13 minus y. And so if I move some things around, I get 9y on the left-hand side, and it looks like I get 9 on the right-hand side. So y is just 1. So there's my point. And now I need to find the slope. To find the slope, I need to know the derivative so that I can find the slope of the tangent line. So let's find dy dx. Okay, so we're going to take the derivative of the entire thing so that we can do implicit differentiation. And that's going to be 2x plus, and just like before, we have another product of functions. Okay, so we're going to have to use the product rule and remember to attach a dy dx whenever we have a y. So basically, we have 2x, that's easy, and now here we have 4x, and then the derivative of y is just dy dx, plus derivative of the green is 4, and then y. Okay, so again, if you forgot the product rule, this is f, this is g, and I'm just going f g prime plus f prime g. That's how I'm getting this down here. Okay, hopefully that all makes some sense. Let's see, where was I? 2x plus 4x dy dx plus 4y equals 13 minus the derivative of y is just going to be dy dx. Think of it as the derivative of y is 1, attach a dy dx because there's a y there, right? So that's where I'm getting that from. Okay, so same as before, isolate dy dx. So I'm going to move everything to the left and factor at the same time. So dy dx gets factored out, leaving me with 4x plus 1 on the left-hand side. On the right-hand side, we're going to get, what is that, 13 minus 2x minus 4y. So dy dx is going to be 13 minus 2x minus 4y all over 4x plus 1. Okay, so now the slope is going to be dy dx evaluated at the point 2, 1, which we found earlier. Okay? And so I'm just going to plug that in to our formula right above. So that'll be 13 minus 2 times 2 minus 4 times 1 all over 4 times 2 plus 1. Simplify that a bit. 13 minus 4 all over 9. So what is that? 5/9 is what I'm getting for that slope. Okay? And so now that I know the slope, the tangent line will be y minus the y coordinate, which was 1, equals 5/9 times x minus the x coordinate, which was 2. And so that's what I'm getting for the tangent line equation to this example here. Okay? So as you can see, the skills as you learn them are not difficult. In fact, a lot of times you learn something new in calculus and it's pretty quick and it's an easy skill. The problem is now those are going to get embedded into different types of scenarios and problems, and they're going to just come up and you just have to know to use them and apply them as they happen. Okay? All right. Thank you for being patient with me. Sorry I wasn't able to be here, but you should be good to go now with this lesson. I hope to see you on Thursday or Friday. All right. Have a good one. Bye.